Hi, today we can study the theory of alpha emission. It started to explain in the year 1928 by Gamow, Gurney, and Condon. In this theory, an alpha particle is assumed to move in a spherical region determined by the daughter nucleus. The central feature of this one-body model is that the alpha particle is performed inside the parent nucleus. നമുക്കിവിടെ ഒരു parent nucleus ഉണ്ട്. Then we are assuming that the alpha particle is emitted from that parent nucleus. Here from this figure, you draw this figure and try to analyze it. Here A represents from 0 to A represents the radius of the parent nuclei. Then this R represents the size of the nucleus, and this y-axis represents the potential energy, and this region 0 to A represents the this energy region represents the potential energy inside the parent nucleus. This horizontal line represents the disintegration energy, and here it forms a potential barrier for the incoming or outgoing particle. Okay. From the figure, uh, the potential energy shows the potential energy between the alpha particle and the residual nucleus for various distances between their centers. Horizontal line Q is the disintegration energy. This horizontal line. Note that the Coulomb potential is extended inward to a radius A and then arbitrarily cut off. Okay. The radius A can be taken as the sum of the radius of the residual nucleus and of the alpha particle. That means this is the size of the parent nucleus, and it is the sum of the residual nucleus plus the radius of the alpha particle. There are three regions of interest. The spherical region, this is the spherical region. We assume that the parent nucleus is spherical in shape. So the spherical region R less than A, this region, we are inside the nucleus, and where the potential depth is minus V0, and here the potential is minus V0. V0 is taken as the positive number. Classically, the alpha particle can move in this region with kinetic energy Q plus V0, but it cannot escape from it. Classically, the alpha particle cannot escape from this potential region, potential web. Then the second region is the annular region, annular shell region. That is where R, the size R varies in between A and B. This region, okay, second region, where it forms a potential barrier because here the potential energy is more than the total available energy Q. Classically, the alpha particle cannot enter this region from either direction. Okay, classically, alpha particle cannot enter into this region from this side or from this side because of the height of this potential barrier. Just as a tennis ball dropped from a certain height cannot rebound higher, In each case, the kinetic energy would have to be negative. The region, then the third region is greater than R greater than B, this region. So we have three regions, first, second, and third. This region where R greater than B is a classically permitted region outside the barrier. From the classical point of view, an alpha particle in the spherical potential well would sharply reverse its motion every time it tried to pass beyond R equal to A. Quantum mechanically, however, there's a chance of leakage or tunneling through such a barrier. Classically, when a particle starts to move from here to this side, it cannot escape from this potential well. But quantum mechanically, there is a possibility of tunneling through this potential barrier. Oh, the barrier accounts for the fact that alpha unstable nuclei do not decay immediately. The alpha particle within the nucleus must present itself again and again at the barrier surface until it finally penetrates. അപ്പോൾ ഓരോ സമയത്തും ഇത് ആൽഫ പാർട്ടിക്കിൾ നമ്മൾ ഈ തിയറി അനുസരിച്ച് നമ്മൾ പറയുകയാണ് ഇറ്റ്സ് ഹിറ്റ് ബാക്ക് ഹിറ്റ് ആൻഡ് ബാക്ക് അങ്ങനെ ഇത് ആ വാളിൽ ഇങ്ങനെ ഇടിച്ചുകൊണ്ട് ഇങ്ങനെ കണ്ടിന്യൂസ് ആയിട്ട് ഇറ്റ് ഈസ് നോക്സ് അങ്ങനെ പറയാം നമുക്ക് ഡോറിൽ ഇങ്ങനെ മുട്ടിക്കൊണ്ടേയിരിക്കും പുറത്തു പോകാൻ വേണ്ടിയിട്ട് it will not open. Classically, the door will not be open. But quantum mechanically, finally, it penetrates, it tunnels through the barrier. In 238U, for example, the leakage probability is so small that the alpha particle on the average must make approximately 10 power 38 tries before it escapes. In the case of uranium 238, alpha decay നടക്കണമെന്നുണ്ടെങ്കിൽ the alpha particle must at least it should knock the door at least 10 power 38 times. 10 power 38 times door knock ചെയ്യേണ്ടി വരുന്നുണ്ട് എന്തിന് alpha particle to escape from the uranium 238 nucleus. That means it is about 10 power 21 knocks per second. It is almost 10 power 9 years. അപ്പോൾ യുറേനിയം 238 എന്ന ആൽഫ പാർട്ടിക്കിൾ എമിറ്റ് ചെയ്യണമെന്നുണ്ടെങ്കിൽ the alpha particle has to knock the door for continuously 10 power 9 years. The barrier also operates in the reverse order. അതായത് നമ്മളിപ്പം പറഞ്ഞത് ആൽഫ പാർട്ടിക്കിൾ എസ്കേപ്പ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ്. യുറേനിയം 238 10 power 9 years കണ്ടിന്യൂസ് ആയിട്ട് ഇങ്ങനെ ബൗൺസ് ബാക്ക് ചെയ്തെങ്കിൽ മാത്രമേ നോക്ക് ചെയ്തെങ്കിൽ മാത്രമേ ഇറ്റ് കാൻ penetrates through the barrier. A reverse കൊടുക്കാം. When an alpha particle tries to enter into this nucleus, it has to pass through the barrier. Classically, it is not possible to climb this height. Okay. Quantum mechanically, there is a chance of tunneling. The barrier also operates in reverse. In the case of alpha particle scattering by nuclei, alpha particles incident on the barrier from outside the nucleus usually scatter in the Coulomb field if the incident energy is well below the barrier height. Tunneling through the barrier so that the nuclear force between the particle and target can cause nuclear reactions is a relatively improbable process at low energy. The theoretical analysis of nuclear reactions induced by charged particles uses a formalism similar to that of alpha decay to calculate the barrier penetration probability. The disintegration constant of an alpha emitter is given by the one-body theory by lambda equal to Fp. F is the frequency with which the alpha particle presents itself at the barrier, and P is the probability of transmission through the barrier. The quantity F is roughly of the order of V by A, where V is the relative velocity of the alpha particle as it rattles about inside the nucleus. We can find V from the kinetic energy of the alpha particle for R less than A. Estimating V0 is to 35 MeV for a typical well depth gives F equal to 6 into 10 power 21 per second for Q equal to 5 MeV. The Coulomb barrier has height B equal to at R equal to A, B equal to 1 by 4 pi epsilon 0 Z into Z prime E square by A. In this expression, alpha particle has energy has charge ZE and the daughter nucleus provides the Coulomb repulsion has charge Z prime E, that is Z minus ZE. The height of the barrier thus varies from B minus Q. Above the particles energy at R equal to A to 0 at R equal to B. And we can take a representative average height to be half B minus Q. We can similarly choose a representative average width to be half into B minus A. For a typical heavy nucleus, Z equal to 90, A equal to 7.5 femtometer. The barrier height B is about 34 MeV. So the factor K2 is about 1.6 per femtometer. The radius B at which the alpha particle leaves the barrier is found from the equality of the particle's energy and the potential energy. B equal to 1 by 4 pi epsilon 0 Z prime E square by Q. And for a typical case of a heavy nucleus with Q equals 6 MeV, B equal to approximately to 42 femtometer. Thus, K2 into 1 by 2 into B minus A is much greater than 1, and we can approximate and the probability equation P equal to e power minus 2 K2 into 1 by 2 into B minus A. The exact quantum mechanical calculation is very similar in spirit to the crude estimate above. We can think of the Coulomb barrier as made up of the sequence of infinitesimal rectangular barrier of height V of R equal to Z prime E square by 4 pi epsilon 0 R and width dr. The probability to penetrate each infinitesimal barrier which extends from R to R plus dr is equal to differentiate that equation dp equal to e power minus 2 dr square root of 2m by h cross square into V of R minus Q. Therefore, the probability to penetrate the complete barrier is P equal to e power minus 2g, where g is the gamma factor that is equal to square root of 2m by h cross square into a power b V of R minus Q into whole power 1 by 2 dr, which can be evaluated as square root of 2m by h cross square Q Z prime E square by 4 pi epsilon 0 R cos square root x minus square root of x into 1 minus x, where x equal to a by b is equal to q by b. The quantity in this bracket is approximately pi by 2 minus 2x power 1 by 2 when x less than 1, as is the case for most decays of interest. Thus, the result of the quantum mechanical calculation for the half-life of alpha decay is T half equal to T half equal to 0.693 into a by c square root of mc square by 2 into v0 plus q e power 2 into square root of 2 mc square by h cross c whole square q into z prime e square by 4 pi epsilon 0 into pi by 2 minus 2 square root of q by b. Even though this oversimplified theory is not strictly correct, it gives us a good estimate of the decay half-life. Okay, നമുക്ക് ഇവിടെ നിർത്താം. അടുത്ത് നമുക്ക് ആംഗുലർ മൊമെന്റം ആൻഡ് പാരിറ്റി ഇൻ ആൽഫ ഡീക്കേ അടുത്ത ക്ലാസ് നോക്കാം.